morning. I'm Marquez, this is Omar Vichot, and that's Mazquiaran, and we will be presenting the second part to the automation of the cheese rolling automation. The problem statement. IAB came to us and asked us to automate an entire process, which went from start to finish, starting with the first game and ending through us where we have to dampen the dough so that the cheese adheres. We need to slightly press it down while not having that stick to whatever mechanism we use to stamp it down. We have to spread the cheese on both sides, and at the end, roll it in a specific way called a twist that is signature to this product from IAB. This is a very slow process, very labor-intensive process. We were asked to automate it because if we could increase this production, the demand will be there to match it, as assured by the company. We will reduce costs by, of course, increasing the production to 500% more than where we are now, which is 11,000 per week as opposed to 11,000 per day. This is the process as it is now. It's manually wet. Now the cheese is poured on top, and then stamped manually, and then rolled individually. So, again, very labor intensive. We hope to remedy this with our machine.
Okay, so some design specification that we've been looking into for the machine is basically using stainless steel 304 and 316 where there might be possible food contact. But also, the main reason for this is for bacteria prevention and corrosion resistance. For the conveyor belt, we're going to be using an FDA approved belt that's also oil resistant. And it's easily clean, and again, our main concern is to prevent bacteria because there's going to be constant cheese on one of the two conveyor belts that we're going to have. And we want it to be modular, so it's easily repaired. Parts, you can find them in stock, so you can repair the machine if in case one part fails. And we are going to be using mild steel, but we're going to be powder coating it to meet FDA standards in areas where there's not going to be any possible food contact. Okay, so our initial design, before we thought that both machines were going to just need 2 operators. So we assumed this model. So we throw cheese initially on the machine. The cheese stick will fall. Then another cheese hopper would allow cheese to get on the other side of the dough. Then there will be pressed down a bit to make sure that the cheese adheres to the piece of dough, and then it'll go through a chain mill. And then 2 rollers to give it the final. The chain mill is to give it the twist, and then the 2 rollers to give it the final stretch to elongate the cheese stick. This one is our second design, and the main difference compared to the first one is how the mesh was adjusted. So the previous one, we were going to set the machine about 45 degrees off from the first group's machine. Here we just wanted to put them in line to take up less space. And that's the reason why we use the stainless steel mesh at a 45-degree angle. And then due to constraints that we had in trying to separate the pieces of dough from one machine to the next, it proved to be a little bit difficult since the other group is firing about 4 or 5 slices of dough at the same time, and one following the other. So then our design here just requires 2 operators, so it's still going to be somewhat labor intensive, but it's going to be the process of rolling the dough, applying the cheese is going to be a lot faster than if it were done manually. So our main design here was using a movable top, which underneath there's going to be a cheese hopper. Then the person will put the piece of dough here, it will fall onto a second belt. Cheese hopper will throw cheese on it again. The roller would press down the cheese to make sure it sticks. This is a mount for the chain mill, and then the tabletop would be the part that will provide the final twisting to elongate the cheese stick. this is a basic idea of how our machine would look like. So movable top back there underneath you, we could see a cheese hopper here. There's a water sprayer system to dampen the cheese so the dough adheres. Then the dough here will fall, press against the cheese, the roller will press it down. At the same time, we also have another cheese hopper throwing cheese on top of it. That will go through a chain knot, and then the final twisting done with the table. In terms of standards, we're using FDA standards and OSHA standards. FDA standards would be with the courings that we could use. So the rollers would have a Teflon coring to prevent the dough and cheese from sticking, because that was one of the main issues we had when we were running complete tests. Also, that also tells us the pieces of metal that we could use, the powder coring also available that we could use. And for OSHA safety standards, we're just worried about, since we're going to be using a drive belt, how to prevent that the operator won't have any issues being near the belt. So with that, it wasn't shown here in the picture, but there are covers to prevent any possible contact with the drive belts. In terms of global design consideration, we were looking into a water filtration system. Again, our main concern there is to prevent any bacteria from contaminating the product. The dimensions and tolerances will be given both in SI units and in English units, and product manuals will be provided in several languages.
Here are some initial simulations. This is one of the idler rollers. It is used throughout the final design. It is used everywhere where a drive roller is not, and we have about 6 in our design. We decided to run simulations on these because the initial approach to the prototype was to build something full scale, but as we quickly found out, the cost of that full scale machine prohibited that. So here we ran a worst case scenario in which the belt, which we got the final breaking strength from McMaster, of a polyurethane belt, something very comparable to what we use, to pull on half of this roller where the bearings are supporting it on the outside. And we got a stress of, excuse me, I'm so sorry, next one please. We got a stress way less than the yield strength of the material, and we, for this one, got a safety factor of 6.4. Go back a slide, please. The displacement was around the magnitude of about 3 to 5 thousandths of an inch, where this wouldn't cause an issue with, say, belt tracking or pinching the roller so that it will not roll anymore. But again, this is a worst case scenario. We don't expect to see that kind of force acting on the roller. Here's another simulation where we designed these hinges so that we could pick up the belt and refill the bottom hopper with cheese. This was one of our designs. We constrained the backside here where a pillow block bearing is going to hold this to allow for the hinging, and we added the entire weight of the movable top to the outside to simulate it being completely vertical, and a displacement of, next slide, a displacement of 20 millionths of an inch that it barely didn't feel it. The safety factor was around 76, so this design can be optimized to reduce some weight and maybe change the material. We saw such a high safety factor because of the material selections as well. Because dictated by OSHA, we need to use stainless steels, we need to use bacterial prevention materials that will not corrode. These are the shafts that are going through these rollers. This is not an entirely accurate simulation because it will have the thicker roller on the outside, which will keep this interior rod from bending as much. 34 thousandths of an inch is a little unacceptable for a support shaft. This is a factor of safety still above 2, but again, simulation is.
Okay, so for the prototype design, since we weren't able to build the full-size scale machine because, first of all, we wanted to use the food-grade belt available since it's oil resistant and it provides better traction. One since we're using two belts, the longer belt was going to cost more than $2,000 already produced by a company. Our budget was only $1,850, so right there we could see that the belt wasn't going to be an option that we were able to buy. So then we were loaned a machine from the company, and then based on there we did a small scale version of the large scale machine that we're designing. So our main concerns was using a roller to flank the cheese onto the dough, the adjusters for the roller and mesh, and then also the table that we're going to be using to provide the final twist and elongating the cheese stick. Stainless steel mesh was also provided by the company. There were two different ones, so we also ran different tests. There was a lighter one and a heavier one. And then for the water application systems, we're looking into trying to implement a filtration system to use with the spray that we have on the full-size scale machine. So this is how our prototype looks. So we have the cheese hopper at the beginning. Originally we already have cheese on the belt, assuming from the bottom cheese hopper to the top of the machine. We place the piece of dough on top. We pass it. The cheese hopper will throw cheese on top. It'll pass through the roller. Once there, it'll catch into the chain mill, and then it'll pass underneath the table to get that final roll. And of course, one of the important factors was how do we place the dough so it could get the initial twist that we need. So here we have our final, our prototype design. So we made the table so it could be adjustable. The roller, we had a few issues because we used aluminum, we didn't use Teflon. So we just put a piece of wax paper to prevent it from sticking as much. And the testing variables that we looked at is whether it matters how you actually place it, whether on the left side would be the leading edge or on the right side. The table height adjustments, we went from 1/2 inch to 3/8 to make sure which one gives the proper final twist. The table surface, whether if a rough stainless steel mesh underneath, very thin, would give a better twist or just a smooth surface. The mesh weight, whether light or heavy, since we were provided with two mesh, one was heavier than the other. And the velocity, we adjusted the belt speed since the conveyor belt had speed adjustment, and it would range between 36 to 66 RPM, which would translate in between So we found the sweet spot of the machine to be, I believe, 45 RPM, I think, or 42, which would give us a 54 feet per second. Per minute, yeah. So the best test settings that we had was the cheese stick had to be leading edge on the left side. The table had to be 1/2 inch from the belt. Smooth table surface. The lighter smash was going to provide the best twist due to the belt that we had, which wasn't oil resistant, and we were having issues with the dough slipping on the belt. 52 feet per minute, best velocity in around seconds, and the average time would take about 3.2 seconds from input to final output in rolling the cheese stick. And consideration is, we saw that sometimes when it would exit the table, it didn't look as the client wanted to, so we would put it again through the mesh and table, and that would give a better result. So that's one of the considerations, that we might need to extend the table about 4 more feet to provide an additional table and mesh. Belt surface needs more friction, that's why we are looking into a food grade belt that's oil resistant and has like a perforated surface, so it could actually grab onto the dough. And then the cheese texture, that wasn't our issue that we were having, was providing too much grease. Again, it all has to do with the belt. After 1 or 2 trials, we were already having issues that it would slip, so we had to be cleaning the belt continuously since it was smooth. And here we can see that the best angle, 60 to 55 degrees. Left side will go first. into the machine so it could provide the best twist that we could get.
Okay, I'm going to talk about the cost analysis of the machine. First, that we found when we were trying to assemble the machine that was too expensive, and it's out of the budget that we have for the $1,800. So then we made the prototype. As we work with the prototype, Vichot lent us a belt that is valued $2,500, and the mesh is around $300. So those two items was not included in the actual cost design because it was too expensive. So the main parts that we were using in our system was some couple of bearings that we use, footbread bearings that we got from the masters. A lot of beam steels, stainless steels that we cut and weld them together so we can assemble the supports and the base to put it around besides the belt. We also have the freshwater pump, some steel flats, and some tools, spare parts, nuts, and everything. Here's the cost analysis. We actually have the $33,000, but that's including the labor. We didn't put the labor in the expenses because it was around 70% of the budget, because it was around $1,500. So the product expenses was $2,000, and we were saving. So for the water system, it was around the 20% of the whole budget. The most expensive part that we were using was the steel beams and all the parts that we put to assemble the actual product. Here's a schedule of what we were doing during the whole year. We start with the topic selection, the research and design, and we finish up with the final presentation and the actual prototype information. Here's a small video about how actually the machine works. First, we put the cheese stick. It went to the hopper, the cheese go into the dock, went through the mesh, and then through it. Here's part by part. Here are some guidelines that we put on the belt. So the worker, when it's going to put the cheese, he put it in the right position. Then here's how the hopper works when you release the cheese into the system. Then here's how the process of the rolling works. It's slow motion how the cheese actually rolls. Then we have finished around the flattening table, so we can have the actual cheese taken here. Okay, as Omar told before, we have sometimes to put the cheese stick a couple of times to the same belt, so it can actually find the length that we were looking for, so we can certify for applying the style. Here's the final product that we actually did through the testing. Okay. Here are some photos of that video that were actually, because it was already too fast. So here's the actual prototype. Here are some the guidelines that we actually put in the belt. So it wasn't, so the worker when he's going to put the cheese stick, he doesn't make a mistake and he put the correct direction of the dough in the belt. If we don't put the cheese stick like this, we might get the wrong measurements and the wrong final product. Okay, here's a picture of the hopper, how it works. We put the cheese in there. When we turn it around, we release the cheese. Here's a photo of Steven with our actual final product. For future work considerations, we should look into increase the production of the cheese stick to be a little bit more automatic. We can actually use this machine to produce other products because all of the parts are adjustable. We can we can increase the height. So we can actually make some bread, not only cheese sticks. All our parts are modular, so we can actually remove them, clean them, and then we can put it again. Okay, we were finding too much trouble with the cheese when it was going through the mesh, because the cheese it got stuck into the mesh. So we just have to remove it, clean it a little bit, and we can put it again. As Omar said, we need to. We saw in the testings that when we pass the cheese stick and we repeat the process from the rolling part, we were applying much desired rolls cheese stick that we were looking for. Here's a poster again. We updated a little bit the photo of the machine. We would like to thank FIU and Vichot for the experience. And if you have any questions, this is all the presentation.
question on your cost analysis. I don't know, you said you did not include the cost of the belt or mesh
No,
because it was
there was a
given to
lane
you.
for us, yes.
But that still should be included in the part.
No, that's what I told, the value of the machine was.
So the value of the whole
Yeah,
thing
the actual value of the
includes-
machine was $2,500, $2,500, sorry. And the mesh, it was $300. We didn't put it in the list.
But I
it was
saw,
$300.
on the list that I saw there. you
Yeah,
had
I
total-
put by the company.
Right, but if I wanna see how much it costs to build that, you should include that in there. And then say, we paid this much, you know what I'm saying? I mean, I didn't see the total cost of it, because if you didn't tell me it was 2,500, you look at that chart, it says company.
No, but actually,
Oh, you do have it?
the actual budget that we spent, well, the company lent us, it was $3,300. That was the actual amount that we spent. You can see here. Here's the further expensive, $2,200, but if we had the actual belt, it will raise to $5,000.
Yeah, but you said that the belt was $2,500, right?
Yeah.
And $300 for the mesh, that's $2,800.
$2,800 plus the $2,200 that we actually spent on the first
Right,
parts.
but I don't see the total as being 5,000 something, you know what I'm saying? So I just wanna know how much would that have cost? So just add 20,
Yeah,
$2,800. That's just my point. I mean, if I'm looking at that, I would like to see the actual cost that it would take to build that, as opposed to, not everybody's gonna have a company give you $2,800 to do that. So it's just a little thing.
And I wonder if you guys considered having that last portion of, as you're mentioning that you have problems with the cheese sticking in the mesh. Did you consider during the design process, instead of a highly friction-based type of compounding method to roll this thing, instead of a mesh, either a combination of twisting belts or rollers with twisting belts so that you can roll this differently, or any other type of smoother friction component in that element? Because right now with that chain link, on top of it, it seems like they kind of want to scrape the cheese out rather than leave it in, depending on how the dough quality is, right? If you powder it too much, it won't stick, but if you oil it too much, it will stick too far in, and when you scrape it against that screen, it's gonna yank it off. Hence your cheese, you're gonna be consuming a lot of cheese and then cleaning this thing. I wonder if you guys did conceptually idealize that at the beginning, that you were gonna have this problem.
We did. We looked into several other types of designs, one involving a wedge to begin the twist as well. We opted to go for something that we could manufacture here at FIU to have a working prototype. But as you say, it's something to look into for the future, because it is a concern for the chain when it's stuck with cheese, filled with cheese.
I personally thought the chain was genius. That did a really good job, guys. But the questions I throw out are tied to the feedback from the machine prior is 5 across, coming off a conveyor, and your system requires you to pull one and place it at a given angle to be able to use the machine, and you've got a requirement to take it from 13 seconds down to 2.5. How do you envision you'll solve that kind of an issue?
So we approached the company with that same concern that we could not separate the 5-up configuration that they were giving. So what we ended up with was laying them on baking pans, placing them down and having a worker pick 2 at a time and laying them down in angled position, since our belt is going to be about 24 inches across. And that 2 every 5 seconds gives us that number.
Including the operator's time, you still meet your...
Yes, we
design
actually were at the company and we timed a worker picking a product called a pan de queso, which is just grab, place, organize, flatten, and it took him less than 2.5 seconds.
to the end of the system. Okay, the next fellow. You said that you've got the best settings at a certain.
Right.
What was your defined outputs that we could measure that would tell us that they truly were best settings?
I mean, one of the main concerns for the product is to make sure it has enough cheese in the center, because there's no point in no cheese in the center and when we don't.
So how much cheese, did you quantify how much cheese was a good output versus a bad output?
I mean, we were able to see the difference when there was no cheese in the center.
Well, no and some, okay, I can do that, that's binary. But you're setting all of these parameters.
Right.
I want to know that best practice created exactly what the design of the finished cheese product would be. Did you do anything like that?
I mean, when we tested it, the owners were there. Since we were mainly concerned what the owners wanted. Once they saw that the final product looked like how their manual labor did, that's when we assumed those conditions were the best. But also when we opened them up, we could see that there was already cheese in the dough. When we were running the few other tests, most of the cheese would stay in the chain mill, and that was mainly caused by the belt. So by dampening the dough initially, which is already done in the original in the full-size scale machine, that provided enough traction so it wouldn't slip when it entered the chain mill.
Okay, and then last questions here. Two areas I want you to talk to. One is friction. Does the dough change with time? Is there any controls or constraints around that? Because you're dampening on one machine and then it may sit all night before it gets processed.
No, because that's is going to be a follow-up process. Once we get the dough from the
So all of
first
the
machine,
dough
yeah.
has to be used up
At
on,
the beginning of the project, we were looking into do an automated system between this machine and the other machine. So the transfer between the first stage and the second stage, we were looking into an automatic way to do it. That's why we start with to design.
but I would assume that you would then define what the input dough has to look
Yes,
like to
well,
ensure optimized output from your
when
machine.
they gave us the first stage,
Yeah.
once they finished cutting the dough, we were going to use that dough to put it right into the machines. We're not going to wait, they're not going to wait like a couple of days to put it in there.
Okay.
As you see in the first video, when they cut the dough, that's an immediate process. They actually, the whole video, they cut the dough. And then right after they cut the dough, they just put the cheese and spray the water and they do the twist.
But I mean, reality is they go to lunch, end of shift, and they've already made the dough. You know, that question. Okay, the second half of that question is the cheese. Did you do anything to control the excess cheese and reuse of the excess cheese?
In the final design, we do have a system in place to recover the cheese that stays in the belt. It consists of a pan. We found that the best way to do it was just a pan at the end, right where the belt tapers off, not tapers off, but just drops off. The majority of the cheese falls there. Omar added a scraper a little bit further back to continue catching cheese, whatever may be stuck on that belt, which we don't expect any because the polyurethane is, although it does have traction, it doesn't stick because of the inverted pyramid texture that it has.
Okay, thank you.
I'm going to ask you a question I asked somebody earlier. You came up with $1,500 for your labor. Did you keep time of what you guys spent, outside of the engineering part, but the actual welding, bolting it together, the actual time it took you to do that?
The manufacturing time we did not keep count on. However, the $1,500, that figure we grabbed it from FIU themselves. They have a system in which funded projects give $500 to the students which complete the project to further time. You're compensated for the time.
But, okay, I want you to build me one of those machines. What are you going to charge me? Forget FIU. Because
Well, we are that part in the project because that was the negotiation at first. But if we're going to, we have to calculate actually the labor.
We have to calculate that because
But you have an illusion up there right now because you really don't know what it really cost you to build that particular machine. Right now, the $1,500 at $100 an hour, that's only 15 hours. And I'm guessing you put a lot more than 15 hours into that part. So you really got to be careful. It's number one reason of small business failure is they only have one customer. The number two reason is they don't keep time on what it took them to really build the product. So it's very important to do that. The parts are fixed. you know exactly what they are. But your labor can be all over the place. So, I don't like the estimate. It really warps the price of the product.
Steve, please. You can come here if you want.
Yeah, quickly,
Yeah, of course.
I'm gonna address, be very brief.
Sure.
My name is Steve Saperstein. Good morning to all of you. I represent the company. We've been with the engineers through the whole process. It's been very fun to watch them do what they present today. And I think I'm going to answer your question. You're right. I mean, the dough, the piece of dough that we use is a live item. You know, if you leave it for too long, it will grow. It will not be good. So the transfer between the first stage to the second stage has to be very quick. Now, FIU and the engineering department needs to know that we're missing the middle part, which will be the one that will take the little pieces and put them to the roller. That's another project for you. So, but anyhow, doing this, it was great to meet Professor Tosunoglu. It was very helpful. He helped us through the whole process. And for you to know, we're a company that produces, everything is bakery products, they're frozen. Most of our machines, most of the whole process and all the products are automated by now. But this one, as you saw in the video, is a very artisan type of deal. And when the students came to us and asked, hey, how many palitos de queso, because that's the name of the product, you do a day, you know, we were telling them, you know, forcing the girls that they work at the most 11,000, but they say, no, we're gonna make a machine that's gonna do 11,000 in one day. That was very attractive to us, because basically it's a product that we have such a big demand that we cannot fulfill the orders because we're not automated. So this is it, there you have it. The only thing none of the students mentioned is that how good the palitos de queso were.
And you didn't bring any here.
That's great, but for the next step, the third one, I promise it will be on the table. All right?
That's
Thank you
incentive.
much.
Thank you.